In this video, I'll be explaining the chamber configuration options in UniformityPro 3D. Now when you open up UniformityPro, you're given this big display with lots of different panels. I've got a big 1080p monitor, which makes it really nice that I can kind of see everything at once. If you have a smaller monitor, that's okay, and in a separate video, I'll introduce this panel manipulation. But for right now, we'll just kind of leave everything up. Getting a quick bird's eye view, on the left we've got sources, chamber, parts, two chamber maps, a targets panel, masks, and optimizer and variable settings. Then over here on the main part we have the uniformity plot, and then a couple of tabs up here. Chamber geometry, and then a 3D chamber map, which I'll come back to in a second. And also kind of tucked away here I've got a plume plot, and I'll explain that later. But just wanted to give you a bird's eye view of everything. So kind of first things first, on this uniformity plot, that's kind of where we'll be spending a lot of our time watching things change. And there are two big options. There's the surface uniformity, which we could explain as sample points over the two-dimensional surface. And that's as opposed to, if I come up here on the targets panel, I can change the type from uniformity surface, and uniform spacing is just the default one. It just makes it easy to get some basic settings looked at. And then up here I've got uniformity radial uniform spacing. So I'll click that, and you'll see this panel now changes, and I'm going from minus row to row of my part, and then here's the uniformity from point A to 1.2. The red dots are my uniformity targets, which are 1. So radial targets are only along the diagonal, so that's kind of a setback there versus the surface targets that lets you see more of the whole part. But because radial targets are fewer in number, they're consequently faster to calculate. And radial targets, this plot allows you to view separate sources plotted simultaneously. So if that's what you need, then radial uniformity is what you want. But surface uniformity is really nice that you can see across the whole part. So I'll leave it on surface uniformity for now. Much of what I'm going to explain in this video is actually accessed through tooltips if you want a kind of reminder. So to get to that, you click Help, and you can say Enable Tooltips. And now you'll see when you pause over things, it'll come up with these tooltips. But if you're familiar with what everything does, they're kind of annoying, they get in the way, and so they're off by default, and you can just disable them or enable them as you need to. So if you need a quick reminder, you can just enable the tooltip, see what something is, and then turn it right back off again. So let's start looking at these chamber maps here, because again, like the uniformity plot, it's what we'll be watching as I take you through the different options. So we've got two views. We've got an XY view and an XZ view. The XY view down here you could think of as a projection on the chamber floor of the planet, the part or parts, sources, and masks. And then over here we've got the XZ view, or the profile view. And this is a profile of the planet, parts, sources, and masks. So they're great because when you use the two views in tandem, you can really get a good idea of that everything you've entered here is the way you intend it. So the purpose of this is really just a visual confirmation that these settings are input correctly. Or at least you understand, and that you and the program are on the same page, essentially. We've also introduced this slider here that enables you to take the planet through, in time, through the first orbit of your run. And we define an orbit as the center of the planet going around the chamber one time. So if I take this and just drag it along, you can see both plots are moving identically through the first run. Or excuse me, the first orbit. So I say this is really nice just to kind of help you see that things are moving the way you want. Also, when you have tilts and things applied, it kind of helps you with perspective, since these are just projections. But to also help with that, we introduced a 3D chamber map in this version, which if I pull it up, I can click here, Render 3D Chamber Map. And it generates or renders a 3D chamber using the same settings and colors that you see here, but this is totally interactive. So using the center mouse wheel, I can zoom out or zoom in, and then if I take the right mouse button and hold it down, then I can rotate around a point. And you can see around that there's kind of a faint circle around the blue square at the center of this plot. That happens to be the source that I've got going, but you can see I'm rotating about that point. If you want to change that rotation point, you can let go of the right mouse button, hold down the middle mouse button or the wheel button, and now you can move things side to side. So if I want to kind of move it up here, let's go up a little higher. There, see now essentially I'm rotating about this part on the planet. So this is a really, really useful tool. Again, used in connection with these to help you just kind of be convinced that your chamber is set up correctly and you understand exactly what's going on and what's being modeled. The reason why we put it over here rather than making it the primary view is it takes a long time to render these 3D models. It doesn't take that long, but it takes a lot longer than these. And when you're optimizing and you're just going through, you don't want to be tied back by time. And so what I would suggest is just kind of have it available so that you can refer to, but I would leave this checked by default, which turns off that it's going to auto-update. Now if you undo this, and I can kind of confirm, see the other two are moving when I move the slider, but this one's not. But if I uncheck this, now this is going to be updated at the same rate as the rest are. And in this case it's pretty quick, but there also is quite a bit of a lag. So just so you know, that's what that's there for, but you can always, when you need to, re-click the button and that'll re-render where you need it to, and then you can interact with it. Okay, moving on from that, kind of back over to these two chamber maps. You can see when I move one slider, it moves the other two sliders too, and that's just to kind of keep everything on the same page. Now a couple other things. So this blue circle is representing the source that we have. And then the green is the planet, or the planetary. And then here I've got a black part. And this blue dot is the point on the part that I'm kind of referencing. So let's break that down a little bit. Here I've got an XY, and that identifies a point on my selected part. So over here on the parts panel, right now I only have one part, and I'll show you in a little bit that I could have multiple parts. But so this XY is referring to the point on the selected part in this list. And the XY is in the coordinate system of the part, and it shows the surface normal at that point. So this coming out here is the surface normal at that point. If I had a curved part, you'd see as I changed the X or the Y that this would change with the normals we'd expect it. We also get a line of sight going from that point to the selected source. So just like I can have multiple parts, I can have multiple sources as well. And those will be in a list, and again I'll introduce that a little bit later. So we've got the line of sight from the selected source to the point, and then if you check this box you'll also see the path of one orbit at that point. So I'll check the box down here, and this shows the path that this point is going to follow through its first orbit, and I can have it on one or both of them. And so if you watch, I'm looking at the center of the part, and sure enough it's following that line just as we'd expect it. So if I change the point on the part, this is a 2-inch part, so let me put it out at 1, x equals 1. You can see that changed the shape there a little bit, and it's because the point's taking a different path. This minimum plot width, it's just a minimum width of either axis. It doesn't have any reference to your actual size of your chamber or anything. It's just for plotting convenience. And the other axis adjusts to maintain equal grid spacings. So you can see I can zoom in and out here. And a neat trick I want to show you is right here on this down arrow. I can click this and go up to plot focus. And right now the plot focus is the chamber middle. But I have lots of options available. For instance, let me do the part point. And now the center of this plot is going to be this plot point. So as I zoom into it, everything kind of comes around it. So this is useful just especially during mass design and things. Sometimes you just want to see different parts of your configuration and zoom in on them and whatnot. And so this is a feature to help you manage that. I'll set it back there for now. Okay, so I want to go back to this uniformity plot panel, and down here at the bottom, you see I have this little panel right here. And this is the number of rotations of the center of the planet. And it's not the total rotations of the planet itself. I'll come back to that when I talk about the gear ratio. But orbits is the number of rotations of the center of the planet. For right now, I'm just going to set this to 1 because it'll make calculations quicker as I'm showing you different changes and options. If you have 10 orbits, then a uniformity calculation will take 10 times as long as 1 orbit. So it's important. But for right now, I can just kind of turn it off, and that'll help things go quicker. The next is this steps per revolution. And this is the number of steps in one planet rotation. Not an orbit, but a rotation of the planet. This number also has direct consequence on the accuracy and the speed of the uniformity calculation. So just a word of advice is I'd start out with a number that's relatively low, maybe 300 or 500, something along those lines. And that'll get you a general feel of the uniformity, especially in the first stages of optimization. But as you need more refinement, then you can raise that number up to 1,000, 5,000, 10,000 even. And that'll help you really refine the edge. If you find that you're having a mask edge during optimization that isn't so smooth, I would just try increasing the steps per revolution. That'll probably help a lot. Okay, then last here we have the normalization. We have a part number, x and y. Now uniformity is dimensionless. It's calculated by the accumulated thickness divided by the thickness at a specified normalization point. So in this case, I'm saying that I want my normalization point to be the center of part number 1. I just have one part, and if I click here, you can see I get a drop down, and of course there's only one option available right now. And that thickness is listed right here, normalization point thickness. Right there. Okay, next I'd like to introduce the source panel. So if I come over here, I've got this first grid, which indicates the number of sources I have loaded. So right now there's just one. If I right-click on the panel title, I get some options. Add new source, duplicate selected sources, or delete the selected sources. I can also get that panel by clicking left on the down arrow or going up here to the sources menu. So we try to put it in lots of places so you could find it if you needed it. But so if I add a new source, you can see now I've got 2. And let me go ahead and delete that one for now. Now I'm back to 1. So if you want, you can give it a name, type. This refers to the coordinate system that used to indicate the location of the source at the bottom of the chamber. So you could either do XY or rho phi. So if I click here, you can see XY now changed to rho phi. Just whatever your preference is. I'll come back to width and color, and then on will turn a source on or off. And when I turned it off, this went to gray, and the optimizer went to not a number, and everything's minus infinity. And you know there's some kind of problem going on. You just check that your source is on, and also it disappeared from the chamber. Oops. Okay, so with x and y, that's referring to the x or y position of the source with respect to the chamber center line. So if I move this to x equals 5 and y equals 10, here's the x direction and here's the y direction. And if I change this to rho phi, now I've got rho at 5 and phi is 10 degrees. We'll make that 90 degrees so we can put it up where we would expect it. And I'll take it back to xy and put it back in the center. Okay, and then z changes the z direction. It's the distance from the chamber floor to the height of the source. So if I make it 10, then it puts it up there, put it back down to 0. Okay, then we have gamma. Gamma is the angle in degrees of the source normal with respect to the vertical axis. So if I change this to, say, 25, I've now got this thick dashed line. This kind of helps you see the tilt and the direction of the source. So it's going out this way, and I can see here in this chamber map that it's going out this way. And that's related to the psi. The psi is the azimuthal angle in degrees of the source normal, and it's with respect to the positive x-axis. So 0 puts you this way. If I wanted to go this way, I'd say 90. I could have said negative 90 to go down the other way. And then, so as I change my gamma, you can see that it changed that tilt angle. So when these are both 0, that dashed line goes away. So you can just assume, if you don't see that thick dashed line, that the source is just going straight up. Okay, now the rate is the relative source rate, and it's used when 2 or more sources are modeled. So when only one source is modeled, it doesn't have any influence or effect on the merit function or the uniformity or optimization or anything. However, if you set it to 0, that's the same thing as turning it off. And you can see the same things kind of happened. But when you have multiple sources, that's an important number to keep in mind. Then lastly, we have the plume parameter. We'll call it plume parameter m, where m is the power of the cosine of the deposition angle. We could say cosine of theta to the mth power, where theta is the angle between the source direction and the line of sight from the source to the part. So, and if I pull up this plume plot, this is in essence a representation of the strength of the depositing stream versus the angle theta. And again, that's the angle between the source direction and the line of sight from the source to the part. So remember that right now the source is going straight up. It's this angle right here. It's theta. Now one thing that I was going to introduce but I didn't yet is this back to the chamber geometry. This kind of helps you reestablish some things and some parameters, and I'll refer back to this here in a second. But going back up here to width, for radial plots, this is the line thickness for the source uniformity. And what's also used in the chamber map plots is the line thickness for the source direction. So if I put a tilt back on here, as I change this number, see that line thickness changes. So it's really just for your benefit and for plotting purposes. And same thing with color here. In the radial plots, it's the line color for the source uniformity. In the chamber map plots, it's the color of the source direction, the line of sight from the source to the point on the part normal at that point, and the path of one orbit. So I'll change it to red. And so this is really helpful if you have multiple sources. Let me go ahead and add another one. So now you can see I've got a blue source and a red source. Let me put my blue source at a different location. So now you can keep track of which one's which. And now I'll show that path of one orbit. You can see it's either blue or red, depending on which source you have selected. You'll also see that that line of sight changes. The path of one orbit, knowing what color it is more important when we have a mask. You'll be able to see what's being blocked by the mask based on which source it's referring to. Okay, let's move down to this chamber panel. We begin right at the top with planet rotation type. Your choices are single or double rotation. Basically, a single rotation would be what we call a dome setup. And you can see that some of the options went away. And right now the planet or the dome is right there at the middle of the chamber. And also the chamber geometry picture changed to kind of help you know what some of these settings are. So if I can change that back to double or single, you can see that changes there. Again, for your own reference and benefit. So we'll leave it on double for now. So I've got the planet height here, which on single is the dome height, and if it's a double rotation, it's the distance from the chamber floor to the height of the center of the planet. And for single rotation, it's the distance from the chamber floor to the center of the dome. So if right now you can see that my planet is up here at 30. If I put it down to 20, now I moved it down there. Okay, and then the big R, that's the distance from the chamber center line to the center of the planet. So my planet center is right here at 10, where I'd expect it, but let me make it 0, and in essence that makes it in part single rotation. But I can put it out at 20 if I wanted to, or 10. One thing I should say is that these units are irrespective of inches and millimeters. It doesn't matter as long as you're consistent. All the calculations will be correct. So it's whatever units that you feel most comfortable in. Now the planet alpha 0, or the dome alpha 0 if you're in single rotation, is the beginning angle in degrees of the orbiting of the center of the planet, or the dome rotation. So right now you can see it's at 0, so I'm starting right here. And if I make it 45, then it'll be up here. If I even hold down these up or down arrows, I can see that change in real time. And then the beta 0 refers to the beginning angle of the planet rotation. And so as I move this, you can see now the planet is rotating in place. So again, this is just the beginning angle, because as soon as you go through the run, it'll proceed from that point. So I'll set these both back to 0. And just to avoid confusion, I'll delete this second source. So just have one, and I'll get rid of the tilt. Okay, down here we've got the planet tilt, and that's the angle of the planet center normal with respect to the vertical axis. So right now 0 would be a flat planet. If I tilt it 45 degrees, see I've got it going out that way. That's 45. The number of longitude and latitude lines is just for graphic purposes, but it can be helpful if you need more definition, just whatever you need. And then down here, the planet surface figure, your choices are flat, spheric, conic, or conic aspheric. And as you choose one option, then the appropriate parameters will appear. So when I click spheric, now I've got the radius of curvature. So if I've got a curved planet, maybe radius of curvature is 20. There you can see the curvature on the planet. I can zoom in, and let's zoom into the middle of the planet. Now you can see that. Positive values will model a concave planet, and negative values will model a convex planet. So if I choose -20, you can see it go the other way. And then other options here. Oh yeah, I put 0, and it wouldn't let me. That was right. So if you want a flat planet, go back to flat. Other options, conic and concave spherical. Just choose concave spheric to see all the options at once. Of course, radius of curvature, and then the conic coefficient. And that coefficient determines the shape. And there's a tooltip here that will appear that you can look at that'll explain how to get a hyperbola, a parabola, a spheroid, a sphere, and all those settings based on what you want or need. And then we've got the 4 aspheric coefficients. And that's the for the polynomial deviation from the base surface for your use as needed. Okay, then down here on the gear method, you can choose either ratio or cogs. If the gear ratio is not known, then you can input the number of sun and planet cogs, and we just calculate for you basically the ratio as being the number of sun cogs divided by the number of planet cogs. But let's talk about ratio for a second. With a ratio of 0, we reference that as meaning that the planet itself does not rotate. You can see here that through the first orbit, it's just static. Now the planet, with respect to the chamber floor, does rotate once, but not independent of its own orbit. And so when talking about the number of rotations, basically we can say that the planet rotates 1 plus the gear ratio for each orbit. That's the number of rotations of the planet. So when setting the gear ratio, it's best to use the slider and just ensure again that it's doing what you expect it to do. And here you can use that path of 1 orbit to help you visualize that. So set it back to 4.456, and there you can see all these different loops it goes through. Okay, the counter rotate, when it's unchecked, then the planet rotation or the planet spin is counterclockwise when you're looking down. So the planet's spinning counterclockwise. When I check it, now the planet will spin clockwise looking down. So notice that for both options, the planet's center orbit is counterclockwise for either option. And these two options require entirely different gear structures. So, but we have both options available for you. And then angle factor is the last one here. And that's normally equal to 1. What it is the power of the cosine of the angle of the arrival on the part. So for some of you, with this, you might have a special need for that. But most of you will just need that to be 1. Okay, then as we move down to parts panel down here, again I've got this box here to help me have manage multiple parts. So I can add a part, or duplicate or delete parts, and then here's a number, and then I can change the color. So let me change the part position. And you see I've got 2 black parts. I'll make one of them, I don't know, blue. You can see that's blue over there, and we'll make the other one light shaded green. That's kind of hard to see, but and then the width changes how thick that outline on the part is. Now that we've got multiple parts, we can go to uniformity plot and see indeed multiple parts plotted here at the same time. Notice the blue and the green consistent with our colors that we set up over here. That just helps you keep your head straight. Down here we've got this plot parts option, all parts or part number. So if I want to see it big, I can click part number and then choose 1 or 2. And then I can just kind of get a nice big plot, or the overview there. Okay, now coming back over to parts, I'm going to lift this up a little bit. Let's look at part number 1. Radial position and angle position. The radial position, it's the distance from the rotational axis to the part center. So right here is where it's going to be coming from. So it's 6 out. If I make it 0, it's going to be right at the center of my planet, or back to 6. And then the angle position refers to the angle of the part center with respect to the x-axis. So if I spin this out to 45, now I'm up here. So you can set multiple parts on different rings or whatever. And then the shape of the part, we've got right here circle. It could be a rectangle, an ellipse if they're not the same diameter in both directions, or even a custom shape. So let's talk about this for a second. So rectangle just gives me this whole rectangle part, and when I choose circle, notice that it just essentially just kind of cuts off the points around. And then instead of here I've got diameter, but when I choose ellipse, I've got x width and y width, so I could make it skewed in one direction. Now I'm going to start to lift these up so I can give myself a little more room. Here, this number of x samples and y samples, that refers to the density of the sample points that we use to assess the uniformity. So if I wanted maybe 11 by 11, you can see now that that's a little more smooth. And I can even go, I don't know, 21 by 21. Let's see what that looks like. You can see the contours just get a lot smoother. Not just the contour lines, but the color contours here. If you have enough sample points, maybe 101 by 101 or more, it takes a long time to calculate, but it gives you a really, really smooth color contour, which is really nice. But again, it is time consuming for those calculations to take place, so just use it when you need it. So let's go back here, and back to this shape. Let's go back to circle for now, because I want to talk about the surface figure. On the surface figure, similar to what we saw with the chamber with the planet, we've got flat, spheric, conic, conic, aspheric, and now toric and toric aspheric. So let's choose a toric, and you can see we've got 2 curvatures, one in the x direction and one in the y direction. So if I want to choose, make this maybe, now let's say 5 and minus 5. Now as I zoom into my part, you can see the potato chip here. These curvatures, this is again where it's helpful to have the slider just to kind of help things rotate in time and help your eye out. These are really quick to make, but again, if you want to see it in this 3D mode, you can. We'll render one right here, and let's have a look at this part. Let's raise the center up. Bring it out a little bit. There, now you can see that part. That's the curvature on it. The curvature mount, that refers to the vertex. Well, if it's on vertex, that's the vertex of the curved part is at the planet surface. So you can see right there is where it's at. Let me switch this to a spheric so we can see it a little more clearly. So it's vertex mounted, you could say. Then if you choose edge mount, see how the vertex is up here above? This is where the planet is, right along 30. So edge means that the position at the radius of the part is at the planet's surface. Consequently, the vertex will be higher or lower than the planet, depending on the sign of the curvature. So if I make curvature -5, you'll see it flip around. And you saw it shift because this plot point is my center. Let's actually make the plot point at 1, and now you'll just see it flip, and the plot won't change. Here now you can also see this normal is adjusting right as we'd expect it to. Now what if these options aren't enough for what you need? Both in the shape and in the surface figure, we have a custom option. You can go down here to Customize Shape and Surface Figure, and this opens up a box, or a window. This is your part. Remember, we've got a 1-inch part right here, and these are the sag values at each of these node points. We've got 11 by 11. I can make it 5 by 5, and there you can see each of the sag values. So what if you want to change the sag values? You can change the surface figure to custom, now in all the zeros, but I could enter in, or probably ideally paste in values here. And then if something was incorrect with the orientation, you can flip the Z or the Y values there. And this enables you to have your own custom surface figure. Now you can see that the shape is still circle, and so these cells are blocked out automatically. I could have set it to rectangle, and that would have included everything. But I can also have a custom shape. And so now I can uncheck boxes. Essentially, unchecked regions means they're not on the part. So if it's going to be an odd shaped part, but here's a rectangle essentially that I've kind of cut out this top corner. If I click OK, you can see here's my shape with that kind of corner taken out. Now this is funky because I had those weird, sag values in. I just want to show you that works. You can also have a custom shape even with a set custom surface figure. A set surface figure, not a custom one. See, the sag values are automatically filled in, and they'll change based in real time. But I can't double click and edit them, but I can change the shape. Now if you don't want to click a bunch of boxes but you have kind of a general starting point, here's some buttons to help get you started. We've got blank, just if you want to start from scratch. Rectangle, that's everything. An ellipse, forms an ellipse there. Lemniscate is kind of your infinity symbol. And then this match starting shape will try to anticipate the shape that you came in with and match it. So I came in with that shape and remembered it. But if you change the number of sample points, say we want to just do 5 by 5, I can click that match starting shape and it'll kind of make a good guess of where it needs to take off some boxes. But it might need some more refinement. But this is a very powerful screen that enables you to really get what you need. Now, one last tip on here is when you have a custom surface figure and a custom shape, you'll need to click Generate Edge Values, and that'll produce more accurate edge calculations. If you just leave unchecked regions as 0, that can mess up as we try to anticipate the slope of a curved part, and it sees these zeros. That'll mess up what it's interpolating. And so click Generate Edge Values, and that'll fill the zeros in the unchecked regions with approximate values. You can refine them if you even have those values, or if you just want to guess of them, you'll need to do that. So I'll click OK there. And let me go back to just a flat circle. Okay, again with the duplicate, say you really like this part, you right click here and say duplicate, and we'll put it out at 3. So here you can have, easily duplicate your parts once you get them all set up. And then I'll select both of them, say delete. Okay, now looking onto the masks panel, if I either use this down arrow or right click or go up to the masks menu, I can add a new mask, and I can turn it on or off. You can see that it's defaulted to a leaf right there. I can turn it off, and you can see the uniformity change just based on having that mask in the chamber. I can give it a name if I want. This defines the upper half type, basically. And we've got 7 different masks right now. And then this lower edge is basically the lower half type. We can have none, symmetric, or same type. So same type means the same type as the upper half, but with its own independent controls. I'll show that in a second, but so if I have a leaf, let me turn it on. Right now it's symmetric. If I say none, I just get the top half. If I get same type, if you look down here, I've got the upper edge length and width and the lower edge length and width. So I'll make the lower edge different for whatever reason. Probably for most cases you want the length the same, but it at least gives you the freedom to be whatever you'd want it to be, and let the optimizer find a solution as well. Or I can we'll just go back to symmetric, and then I can change the width. And consistent with other places, it's for plotting purposes to help you identify it. And I can change the color, and we'll make it orange. Kind of blends in with the red. We'll go dark green. Okay, so here on this left panel, we've got kind of the main locations and not mask specific. All of our mask types use these 5 parameters to help define it. So this row is the distance from the chamber center line to the innermost point of the mask. So you can see here it's 2, and so 2 is right there. If I bring it out at 10, then we'll see it go onto that grid line. 0 would put it there. So this is an important distinction, since a lot of the other positioning refers to the center, like the center of the planet, or the center of the part, or the center of the source. And here referring to the leftmost edge. And so that is a difference from some of our other things. And then also you have a phi, which will indicates the mass position with respect to the x-axis. That's an angle. 45 degrees minus 45 degrees. D refers to the distance below the plane of the planet center to the plane of the mask at rho. So it's 1 down, and let me zoom out of this. And you can see it there. If I make it 0, it's going to be right there on the planet. And if I make it down 10, we'll put it there. So this is an important distinction, because if you do have a curved planet, see, it's always out from, it's the distance below the plane of the planet center to the plane of the mask at rho. So right there. Even we'll take it off center. And it's still down and over. Next we have tilt. This is the angle of the mask normal with respect to the vertical axis and coming out of that point. So I can tilt it down 25 degrees, 45 degrees, And as you see this projection on the planet floor, you see that change, but sometimes when something's got a heavy tilt on it and you're optimizing, it's hard to see what the actual shape of the mask is. And so this is again where I'll point your attention to this 3D chamber map, because this enables you to rotate around and say, oh, okay, that's the shape, and get a good feel for it. Remember that you can always reference the Chamber Geometry tab if you just want a visual reminder of what each of these parameters are and how they're defined. For example, like we were just talking about with D, you can see where it's referencing to, and just if you don't want to read the text-based tooltip, you can come here for a visual reminder. But let's go on to speed factor. So speed factor is the number of mask orbits per planetary orbit. So if it's 0, that just indicates that the mask is fixed in the chamber. So you can watch this X, Y, and see as I'm moving the planet that the mask stays fixed, as we expect. So 1 would lock it in and move at the same rate as the planet. So 1 orbit, the planet, equals 1 orbit of the mask. And it can also go in the opposite direction. If you want -1, and you can even do 1.5 or what have you. So see, it's going a little bit faster. Okay, so now this brings up the fact of something I want to mention, which is this path of 1 orbit. You can see we see the whole path here. When you have the mask blocking the deposition during the run, then you'll actually see part of this line be suppressed. So what I mean, well, let's move this mask into this line of sight here. So maybe we'll move it out to 12, a little more. Sure, like that. And now you can see part of this red line is missing. If I turn that on and off, you can see. And so what that's saying is that at this moment of the deposition, which is in this first part, at this point that we've defined from this source on this part, then the mask is blocking the line of sight from the part to the source. Now sometimes this isn't clear. Here this is kind of obvious. We see it going through this way. But what if the mask is maybe out here? It would look like it's going through the mask, but it's not. So sometimes this parallax effect can be deceiving. So if you want to verify this, you can always go to your 3D chamber map and line up the point on the part with the source, and sure enough, the mask is blocking that. And if we go a little bit further, let's go right on the edge. And we can see, that's where the mask would not block. So here's another place where this could be helpful, just to take away some confusion or maybe something deceiving in these two plots. Okay, let's come back to the masks and their types and properties. We've got the length and the width. The length refers to the length from tip to tip in the x direction. Let me turn my tilting back off and simplify my plot here. And then width refers to the full width at the center of the mask in the y direction. So if I say 10, it's going from +5 to -5. But notice if I only do none as the bottom half, it's just going from 0 to 5, because it's the full width, as if it was a symmetric mask. Next is the conic. When you go from one mask to another that has the option of being able to convert, not all of them can convert from one to the other, but just if we've determined that it's easy enough to do so, it'll pop up with a question if you'd like to convert it. So in this case, we're kind of upgrading, so to speak, the leaf to a conic. It'll keep the component so as to match it. So we'll say yes. And so I've kept the components, and now it's the same shape. But now I can further refine the edge with these coefficients that we've seen in other parts of the code. So we'll move on to wedge. The wedge has these three components: a width, which is the half angle in degrees of the wedge. So if I go 45, you'll see that that's a 45-degree angle there, coming from this x-axis. And then radius 1 and radius 2, it doesn't matter which one's which, but they together define the extent of the wedge in the x direction. The smaller radius value plus rho defines the innermost edge. So the innermost edge is here at 8 plus 0, or 8 to 10 takes us out to about 18. Well, exactly 18 in this case. But if I wanted to, I could make it a sliver like that. Next is an XY table. And this enables the U to define the edge of the mask as a function, where y is f of x. The x values don't need to be uniformly spaced, but they have to be sequential. Now if I change this to 10, it'll actually resort the table for me, and it carried along its y value with it. So you don't have to keep track of keeping them sequential, but just know that that's an important thing, and I can right-click and add points and delete points, insert points. I can change the number up here. And then if I wanted a different one on the bottom, say I wanted this to extend out a little more, then I could, and I have separate controls over both edges. So that's the table, and that's a little different than the spline. See, here's an option where I can convert the table to a spline. You can always go back and forth between splines and tables of the same type. And you just choose the number of points. So we'll say 5 points. And so now I've got 5 points on each half of it. But now these are splines, so actually let me make it 3. And you can see how nice these edges of the masks are. They have to be evenly spaced, and so I've introduced a length option here. Now as I change the length, the x values are automatically generated uniformly spaced. So I go from 0 to 10 or 0 to 8, and changes there. Let's go ahead and make it symmetric. The other nice thing is, by changing the number of points, it automatically finds where it needs to be to keep this shape as best it can. So if I say 5, that'll put a point perfectly on this line. See, the shape didn't change, but now I have more control over the shape of my leaf. So that's the spline. So we have x, y, and then we have rho theta table in spline. So let's look at the rho theta table. This is where, instead of having the function be y equals f of x, this is theta equals f of r. And same thing with the table earlier. The r values don't need to be uniformly spaced, but they have to be sequential. So here I'm going from 4 to 7. So at r equals 4, then I have a 20-degree theta, and it's going down to 7 with a 0. So if I kept that at 20, you'll see this looks a whole lot like that wedge mask that we had earlier. So in essence, this just enables you to have a lot more control. And then rho just moves it out. Let's put our focus back in the chamber middle so you can see what's going on. There you can see I've got this pure nice wedge. I can move rho out a little bit, and it can help explain. So this just moves the whole thing over, but this angle is based around an r equals 0 point, which is wherever this rho is. So it's right here. So as I change that, you know, it's still all, you can trace this line to that row equals 4 point. So just to help explain what it's doing there. Now, let's make this back to kind of our starting one. So you've got this shape. Table can be converted to a spline. And we'll just do 2 points. By the way, if I had said no, it'll load whatever the saved or the previous spline was. If I hit cancel, it'll just return me to where I was. So now I've got the same shape, but a couple different components here. First I have a midpoint of 5.5. That's because with the spline, again, the points are automatically generated, evenly spaced. In fact, let me have some more points so I can show you. And it's generated from plus and minus the width over 2. So 4 divided by 2 is 2. There's our end there. And we're going about a midpoint of 5.5. Now the reason for that is in case you wanted to have something that was symmetric, it's a little easier to see. Well, it's not going to be perfectly symmetric, but you can get the idea there. Anyways, that's the point behind it. But the benefit is now you do get the spline, which gives you some really smooth lines over just the table. If I take it to the table, just a 3-point table would be identical. Now that's kind of a pointy edge. Anyway, so that's the last of the mask. The last thing I'd like to show is on the uniformity plot. We have some different options that I haven't gone over yet. There's the disable auto plot except during optimization. When we optimize, it'll show you the new results that it's getting, but sometimes when you're making lots of changes, you don't want it to update the plot, especially if you have a lot of orbits or a lot of steps per revolution. Sometimes it can get slow if you have a slow processor. So you can click that, and then it will only update when you click plot uniformity. Now, other things is we have the sources in the merit function reports. We can show each or show combined. That's up here in this merit function report. It tells us the overall merit function, the number of targets and variables that we have. We'll cover that in a different video. But then the sources combined, a normalization point, efficiency, I'll explain here in a second, RMS, peak to valley, and then the merit function for this source, or sources combined. If I add a new source, you can see I've got both of them there. If I pull this down, it gives me a little more space. Sources combined shows everything for both sources, but what if you want to see each source as a whole, or individually? You can do that here with their own normalization point, thickness, their own peak to valley, and their own merit function. If I make it shorter, then I can scroll through here. I can also right-click and copy this info to the clipboard if I'd like. And you can turn both of them off if you want. Now, as far as this plot, we can see either the selected source or the combined sources. Right now we're viewing the combined sources. If I click selected, now this shows one source or the other, as if it was the only one that was on. Now, connected to that is if we instead do a radial uniformity plot. Right now I am plotting the combined sources, but I can also plot each source individually. And you can see here I've got a blue and a red aligned with that, and then each of the sources. So like I said at the very beginning of this video, the benefit to the radial plots is that you can plot separate sources at the same time, whereas with the radial or the surface, you have to do this plot source selected source option. But the fact of the matter is you can get the data however you'd like. Once you have the data here, you can right click on this plot and have a whole host of options. You can copy the plot image to the clipboard. You can copy the plot data that's normalized, which is, with 1 in the middle usually, or the unnormalized data, which is simply the points here multiplied by the normalization point thickness. Now, there's also a plot settings option here, which enables you to have total control over everything you see. You can change the contour lines, turn them off entirely. You can change the color palette. You can even have, custom colors, really whatever you want. Let's do the blue, bright red. That's kind of our default. Turn labels on and off, whatever you'd like. Some of these, I know specifically the contour lines, don't update in real time like you just saw here. You have to go through and manually click plot uniformity again. So if you make a change in the plot settings and you see that it didn't update, do that and that'll take care of the update that you were wanting to see. Last thing I'd like to show is about the efficiency baseline. The efficiency baseline is useful at the beginning of a series of chamber or mask adjustments. For example, if you set the baseline with no mask enabled, I'll turn that off, and I set the baseline, everything's at 100%. Now when I turn on the mask, I'll see how much that mask has affected my efficiency, and here it didn't affect it all that much. But you can also target the efficiency if you find it making the mask too big and you want to, it's constantly a game of efficiency versus uniformity, and you'll have to manage that. So in a future video when we introduce optimizing, we'll cover more about targeting efficiency. But that's all for this video with the chamber configurations. If you have any questions, please feel free to drop us a line.